Coming off of the gases chapter, we still have two more physical states to look at in more detail, and that would be with respect to liquids and solids. And we have a chapter devoted to liquids and solids here, but the gases were separate, and that's because gases are different than liquids and solids. Liquids and solids, the particles of them, as we can see right here, they're always in constant contact, whereas the particles of a gas are never in constant contact unless they should collide into one another within that sample. Really, the question here that sort of defines this chapter is, why do liquids and solids exist at all? Why isn't everything a gas? Why don't these particles, whether they're in a solid or a liquid, simply drift away from each other and become what we see here as a gas? Well, we talked about this in the gases chapter, in that there are intermolecular forces between particles. In the ideal gas law, we assumed that there wasn't, but there really is, and these intermolecular forces are always attractive. In the liquid and the solid state, these intermolecular forces hold together these particles so that they do not drift apart. So we have studied the differences between the three phases of matter: gas, liquid, and solid. And just this is more just to reiterate what these comparisons are. Most importantly, in our gas, liquids, and solids that we see here, we want to talk about these intermolecular forces, because that's really what this chapter or this unit of study is about. The intermolecular forces between the particles of a gas are weak, so weak that the gas remains as a gas. The particles remain apart. Whereas in a liquid and solid, they are stronger. In fact, so strong that the particles are attracted to one another and will not drift away. So we're going to talk about intermolecular forces between particles on a particulate level, but also on an observational level. And there are two observational features of liquids in this case. We're going to stick with liquids. We are talking about liquids and solids, but liquids in particular. So these two observational features can indicate the relative strength of their particles' intermolecular forces. This chapter is really all about comparisons. So if I have two liquids and one of these observational features is more pronounced, then that would indicate that the strength of that particles or that liquid's intermolecular forces between the particles are greater than the other one. So these two observational features are called the viscosity of a liquid, as well as the surface tension of a liquid. Now, these are comparative properties, as I said before. Only if the liquid's particles themselves are similar, and we'll look at some reasoning for that as we move along. So let's take a look at viscosity first. By definition, viscosity would be the resistance of a liquid to flow. It does originate from the particles of the liquid, but now we're looking at on a macroscopic observational point of view. And it shows a pot of honey here. Honey could be said to be very viscous compared, say, to water or something like that. Honey pours very slowly. It has a resistance to flow. So in a way, we could say that, well, the particles of the honey have higher intermolecular forces than the particles of water, the resistance of a liquid to flow. So the viscosity is generally greater in substances with stronger intermolecular forces, as we just said. We could say, I mean, another way of looking at this might be with different particles. The particles of honey, for instance, are different than long hydrocarbon particles like those in motor oil. And generally, the particles in motor oil, these long hydrocarbon types of structure, are not as don't have as much intermolecular forces. However, they become entangled. They're so long, these molecules, they become entangled with one another, and that is what carries out or gives us this viscosity in something like motor oil. The other observational feature is known as surface tension. By definition, surface tension would be the tendency of liquids to minimize their surface area. And over on the left-hand side, we can see a general liquid, and these blue spheres here represent the particles of a liquid. If we have a particle on the interior of a liquid, we have the same intermolecular forces from particles all around it, as shown here. However, if we have a particle at the air-liquid interface, the surface of the liquid, we have a difference, for whatever reason, in the intermolecular forces, the attractive forces between the particles, between particles right beneath the surface and particles at the surface as well. So we have differences in those intermolecular forces. The ones at the air-liquid interface are stronger than the ones under the water, and what this does is it sort of pulls a tension on the liquid that we're dealing with. For liquids whose particles have high intermolecular forces, very strong intermolecular forces, surface tension is greater. For liquids whose particles have less or weaker intermolecular forces, this observational feature is less. So these unequal intermolecular forces on the surface particles creates a skin under tension. And if we look at the picture over on the right here, we see what you may see in the summertime on a brook or a pond. We see these water striders, and these water striders literally walk on water, and you can see where their legs come in. They're dimpled into the water. The water actually dimples in, and that's basically due to the high surface tension within water. If water didn't have a high surface tension, these little creatures would just go right through the surface and end up on the bottom. But luckily, that is not the case. Water has a high surface tension, and these water striders can stride across that water. So I've been doing a lot of talking about these intermolecular forces, and there are actually three of them which we're going to be looking at in detail here. And they can particles can have one of these intermolecular forces or all three of them. It really depends on the nature of the particle, which we're going to look at now. So by way of introduction, these three intermolecular forces. The first one is known as dispersion forces. This is of the three, the weakest intermolecular force, but it is exhibited by all particles, no matter what, atoms, molecules of different type of structure, what have you, all particles bear dispersion forces. The second intermolecular force is known as dipole-dipole forces. This is of an intermediate strength within the three, and it's exhibited only by certain particles. Which particles those are, we'll be looking at presently. And lastly, hydrogen bonding. Of the three, hydrogen bonding is the strongest intermolecular force, and it's exhibited, again, just like dipole-dipole forces, by only certain particles based upon their structure. So let's start by going into more detail on what dispersion forces are. As the weakest intermolecular force, it is present, as I said before, in all particles, no matter what, and we're going to see the reason for that. Now, dispersion forces result from what are called temporary dipoles in a particle, brought about by occasional unequal distribution of electrons. Now, we've talked about dipoles and dipole moments before. And a dipole moment is in a molecule is essentially a permanent unequal distribution of electrons due to differences in the atom's electronegativity. And we'll be talking about that a little bit more when we look at the second intermolecular force. But these are temporary dipoles. What is a temporary dipole? It means sometimes that particle has a dipole moment. Sometimes it does not. And the reason for it is we have this unequal distribution of electrons within the particle. So really, any particle which bears electrons or possesses electrons, which is all particles, will bear dispersion forces. So this is why dispersion forces exist in all particles. So let's look at a good example of a type of particle that will bear dispersion forces. Noble gases, in general, are an example of a particle which bear only dispersion forces. And here we have the example of helium right here. And helium is an atom where we have our nucleus here and sort of a boundary within which helium's 2 electrons can sort of frolic around, if you will. And at any given moment, we'll look at various snapshots of time here. At any given moment, perhaps 1 electron is here and 1 electron is here in helium. If we look at another instantaneous snapshot, perhaps 1 of its electrons is here and then the other electron happens to be here. But very occasionally we encounter a snapshot in time where both of those electrons and their attendant negative charges happen to be on one hemisphere of the molecule, or no, I'm sorry, the atom. In this case, look here, we have our 2 electrons with their attendant negative charges instantaneously over on the left-hand side of that atom. That brings with it a basic sort of a partial negative charge over on that side due to the excess of electrons just in that instant. The deficit of electrons on the other hemisphere brings about a partial positive character. Notice how I'm using these words. It's not a positive and negative charge. They're just partial positive or partial negative characters to them. So if we have a few of these, or more than a few, in any given sample of helium where we have this dipole set up, we can ultimately line them up, and we get these weak attractions happening always within some particles of this sample of helium. Most of them, that's not the case. Most of them have a more equal distribution of electrons, but there's always a certain number in the sample that have this dipole set up, so we get these weak attractions. Averaged throughout the sample of helium, that adds up to, or averages out to, a very weak overall intermolecular force between particles. Now, if we look at what we see right here, it isn't always the same helium atoms that carry out these dispersion forces. These only exist for a split second in time, and then those electrons equalize, and we don't have these weak attractions anymore between, say, these 3 particular atoms, but they do occur on other atoms throughout, giving a constant concentration of these temporary dipoles in order to distribute throughout that sample of helium a very weak intermolecular force known as the dispersion force. So we're going to find that when particles bear only dispersion forces, this is important. When we have a particle like a noble gas, any of the noble gases which bear only dispersion forces, their boiling and melting points in comparison to other noble gases tend to increase as the molar mass of the particle increases. We follow as the molar mass goes up, the boiling point or the melting point of that particular pure substance goes up. So here we have our noble gases. In this direction, we have significantly increasing molar mass, as we can see right here. And as we increase in molar mass, that boiling point increases as well significantly. Notice here we're in kelvins, and in Kelvin, so we're still very, very low temperature, which ultimately makes sense because the boiling points of these are so low because all they have are dispersion forces which hold them together in the liquid state. Remember, what is the boiling point? That is the point where we go from liquid to gas. It is that as we increase the temperature of these particles of a liquid, we start overcoming those weak dispersion intermolecular forces with that heat energy and breaking them apart. And that's essentially boiling and converting from a liquid into a gas. So we've defined one particular type of particle, that of the noble gas, that only bears dispersion forces. Let's look at another one. So we're going to end up with only two particles that only bear dispersion forces, and noble gases is one, and we'll take a look at another one right now. Hydrocarbons. Hydrocarbons are examples of particles, in this case covalent molecules, which only bear dispersion forces. Hydrocarbon, again, by nature, is a compound made up of only carbon and hydrogen. And the difference in electronegativity between carbon-carbon bond and a carbon-hydrogen bond, or carbon and hydrogen in general, is very, very small. And thus, we don't have really any dipole moments associated with these carbon hydrogens or carbon-carbon bonds. So let's see how let's see how this works. When we look at a covalent molecule, these lines, as we'll remember, on that covalent molecule are two electron covalent bonds. So what I'd like to do is focus in on one of them. So we'll focus in on one of those two electrons covalent bonds. Right here we have our carbon and our hydrogen there. So, and those two electrons happen to be encircling both the carbon and the hydrogen at some point, some point within there. And just as we saw in that example of helium, every now and then those two electrons, normally they're zipping around both the carbons and the hydrogens, but every now and then we'll have our two electrons on one side of that carbon-hydrogen bond, or the carbon-carbon bond. We're looking at a carbon-hydrogen bond. And when that happens, instantaneously we have a dipole set up, an instantaneous temporary dipole. And then in the next instant, well, it equalizes, and these electrons equalize themselves within that bond, and perhaps another CH bond undergoes a dipole. This is a temporary dipole. It is induced in that CH bond just by the presence where those electrons happen to be at a given time. And here they just happen to be at one end of that covalent bond. So what that does is to start allowing us to get what would normally have no attractions, just like the usual helium atoms. Well, now we start to get attractions between these normally non-attractive molecules, but we get that weak attraction. In a sample of this particular hydrocarbon, only a few of these are carrying out these weak attractions, which we see here. Most of them are not. And in the next instant, these three, the electron distribution has equalized, and they are not weakly attracted anymore. However, another group of these hydrocarbon molecules do have this temporary dipole induced. So this weak attraction, which we see here, is averaged out throughout the sample of this hydrocarbon, resulting in always a few of the hydrocarbon molecules having those weak attractions, always. There's a few of them in there. Globally, what that means in this sample of our hydrocarbon is there's always a very weak force induced within them. So we have this, turns out to be considered dispersion forces. They're very weak because there's very few of them happening at any given time. So just as we saw before, that predictive ability within the noble gases, the higher molar mass gives a higher boiling point, and the same can be said for hydrocarbons. Why? Because of the particles we're going to be looking at, noble gases and hydrocarbons are going to be the only two examples whose particles only bear dispersion forces. So let's look at this predictive quality. Which of the following hydrocarbons would have the lowest boiling point? Which would have the highest boiling point? If these particles only bear dispersion forces, then we look for the one with the lowest molar mass to have the lowest boiling point. Well, in this case, it would be the one with the least number of carbons. So this one here has the least number of carbons, so thus it would have the lowest boiling point. The highest boiling point would be the one that has the greatest amount of carbon atoms within it. That would be this one. Absolutely would be the highest boiling point of those three. And if we had to make a guess, then the one that's left over would have a mid-range boiling point, and it would be a pretty good guess. Okay, so let's go into detail now about regarding that second intermolecular force that we looked at. We've gone through dispersion forces and described it, and dispersion forces can be expressed as temporary dipoles that occur sometimes not, within a particle due to that instantaneous imbalance of electrons, which creates that temporary dipole. Well, now we're moving on to what are called dipole-dipole forces. Now that was intermolecular force of intermediate strength it was greater than that of the dispersion forces, and this is resultant from particles which have a permanent dipole associated with it. Here is an example up in the upper right-hand corner of one that we've looked at before. This has a permanent dipole associated with it. Over on the left-hand side of it, we see these partial positive and partial negative ends of the dipole. Again, that doesn't mean a full charge, but what it does mean is that the electron density within this is now upon this part of the molecule. It's being dragged towards this end of the molecule. Why? Because oxygen is of a higher electronegativity than carbon or hydrogen, so it pulls those electrons towards that upper part of the molecule. More electrons up there with their attendant negative charges makes for a partial negative character. The deficit of electron density down here gives a partial positive character, because we have a deficit of negative charge because those electrons spend less time in that bottom area, if you will. So what ultimately happens, now these are permanent dipoles. They tend to line up with each other's dipoles. So here we have a number of these lined up, sort of positive to negative dipole, and we get a force between them. Now this force is always on in every particle that bears dipole-dipole forces. And the particles that bear dipole-dipole forces are any particle with a dipole moment that we discussed back in a previous unit of study. If it has a dipole moment, it has dipole-dipole forces. So why is it stronger than dispersion forces? Well, dispersion forces in a sample of a substance bearing only dispersion forces, only a few particles within that sample at any given time have that temporary dipole set up. Most particles do not have it. So globally, that average is a very weak overall force between the particles. In dipole-dipole forces, every single particle has a permanent dipole always on, and we get this sort of thing where we get sort of a head-to-tail lineup of these particles all the time. Now, we can look at this. This is a sort of an interesting graphic right here. If you remember, maybe when you were a kid, you got a present that was all these little magnets that you could play with, and they all, if you put them together, it was hard to get them apart because they'd all sort of go pole to pole and stick together. That's sort of like what we're seeing in these particles bearing dipole-dipole forces. It's like these little magnets. So if we have these dipoles that are always on, the positive ends are lining up with the negative ends of others, and the negative ends are lining up with the positive ends of others. And it's sort of like this network of attractions that are always on all the time. So that overall it becomes a much stronger force than what we were looking at before, the dispersion force. And we can see that graphically. So let's look at a way of describing these relative strengths of intermolecular forces between the dispersion force and the dipole-dipole force. To do this, we have to come up with two molecules that will serve as our representative one bearing a dispersion force. This hydrocarbon will do that just nicely, and one that bears the dipole-dipole force. Well, in this case, we have, that was formaldehyde. That was the molecule we were looking at before, and it's written a little differently, but it is the same thing. So again, let's take a look at what happens when we have a liquid and we start adding heat to that liquid. Eventually, that liquid will boil and turn into a gas. What have we really accomplished there? Well, those particles that were in constant contact in the liquid now have been separated. We've overcome those intermolecular forces. That is, in essence, boiling. So it is the boiling point that we are going to measure, or compare rather, not measure, compare between these two different structures, these representative molecules. Why? Well, think of it this way. As heat is added to a particular liquid, eventually that heat energy is going to overcome the attractive energy between the particles, and they're going to break apart and go into a gas. The liquid will boil. So if I have a comparison of two liquids, and one of those two liquids has very high intermolecular forces between its particles compared to the other liquid, if I add heat to this sample whose particles have high intermolecular forces, I'm going to have to add a lot of heat until that extra heat energy overcomes those strong intermolecular forces, a higher boiling point. Whereas my other sample, which has by comparison lower intermolecular forces between its particles, I don't have to add as much heat to that before it just breaks those particles apart because of those lower intermolecular forces. That would be a lower boiling point. So back to boiling point here. A higher boiling point between the particles means the intermolecular forces are stronger. So that's where we're going here. Most importantly, when we're comparing two particles, we have to make sure that they have very similar, if not identical, masses, molar masses. Remember that, because the higher the molar mass is, well, that leads to a higher boiling point. So we need to move away from that. We need to equalize that variable so that the only difference in boiling points can be attributed to these differences in strength of intermolecular forces. So the molar mass of these two particles that we've looked at are just about the same. So one is 30.1 grams per mole, one is 30 grams per mole. That's fine. As long as they're very close, that equalizes that variable, gets it out of the way, and now we just look for our relative or comparative boiling points. So here now we see that difference, a huge difference. In the hydrocarbon, which only bears dispersion forces, we have about a minus 90 degrees Celsius boiling point. But in the similarly massed molecule, which bears dipole-dipole forces, we have it's about minus 20 degrees Celsius. Now, of course, both of these are bloody cold, but we're just looking at the difference, the comparison. We have about a 70-degree difference between these boiling points. That is huge. That is that is a huge testament to the greater strength of our dipole-dipole forces than our dispersion forces. One more thing I would like to bring up here about these. Our hydrocarbon bears only dispersion forces, as we saw before. Now, our formaldehyde molecule, we said bears dipole-dipole forces, but doesn't it also bear dispersion forces? Since dispersion forces exist in all particles. Well, yes, it does. It did. So we could say that the dipole-dipole force is not the only intermolecular force between the particles, but rather the primary intermolecular force, the strongest intermolecular force within there. And I will tell you that even though formaldehyde bears dispersion forces as well, the difference in strengths of those dispersion forces compared to dipole-dipole forces makes the dispersion forces insignificant. The dipole-dipole force, the strength of the dipole-dipole force eclipses by far any sort of contribution by the dispersion force. All right, the last one. Hydrogen bonding is by far the strongest intermolecular force, stronger than the other two that we have looked at. It is present in just certain molecules. And if a molecule bears either a covalent NH bond, an OH bond, or an FH bond, it will exhibit hydrogen bonding. But the force between the particles occurs between either that nitrogen, oxygen, or fluorine atom and a separate hydrogen attached to an NH, an OH, or an FH on a different molecule. Let's look at some pictorial examples here. With respect to molecules that bear fluorine-hydrogen bonds, there's only one molecule. There's one compound that would be, and that would be HF, hydrofluoric acid, because halogens only have one covalent bond emanating from them. That one covalent bond, once it's attached to a hydrogen, and that is it for fluorine and hydrogen as far as anything else they could possibly bond to. So there is only one example of a molecule that bears hydrogen or fluorine hydrogen bonds, and this is it. And where this and it's a hydrogen bond, where that force is between the hydrogen on one molecule and the fluorine on the other molecule. We see that here. The hydrogen on one molecule and the fluorine on the other molecule is the genesis of that very strong hydrogen bond. So whereas there is only one example of a compound with an FH bond, there are an infinite number of possible molecules that somewhere on it bear either an OH or an NH bond. Some examples. So if we look over on the left-hand side, water. Water is essentially one big walking hydrogen bond. It really is, because all it is made of OH bonds. In this case, with our water, we have our hydrogen bonds shown here between, say, the oxygen on one molecule and a hydrogen on another. Hydrogen on one molecule and an oxygen on the other. So we can set up a real network of these OH hydrogen bonds between molecules, and that's ultimately what gives water, for its very small molar mass, 18 grams per mole or so, it has such a high boiling point of 100 degrees Celsius for such a low molar mass. That's almost unheard of. And that's because of the very strong hydrogen bonding network we get when we look at, when we think about water being what I like to term it, just one big walking hydrogen bond is all water is. Looking over on the right-hand side here, some examples of one where we have NH bonds on the molecule. And notice we have a couple of molecules here. There's one here and another one of the same one right there. Now, in red, these dotted lines in red signify the hydrogen bonds, the very strong hydrogen bonds between them. Notice, from the nitrogen on one to the hydrogen connected to the nitrogen on another. That's important. It would never be, say, to this hydrogen on the molecule or this one, because that hydrogen is only connected to a carbon and thus will not hydrogen bond. It's only between what we see is the nitrogen on one with the hydrogen on the other. The nitrogen on one with the hydrogen on the other. We saw that in a different respect on the water molecules over on the left-hand side, and it's the same sort of thing with any molecules bearing NH covalent bonds. Again, we are limited only by our imagination with the types of molecules that we could build that have an NH bond or an OH bond. So let's look at our boiling point comparison again. This is what we saw previously between a representative molecule which bears dispersion forces and a representative molecule which bears dipole-dipole forces. We had equalized the mass, the molar mass between them, so that that variable was out of the way, and then we were able to compare the boiling points. We saw a vast difference in these boiling points. Well, let's now rope in and bring in a representative molecule which bears hydrogen bonding. And in this case, I know this molecule has hydrogen bonding as its primary intermolecular force because we have an OH covalent bond on it. Could have an NH covalent bond on it. That would also bear hydrogen bonding. But we picked this one because its molar mass is very, very similar to the other two. 32 grams per mole is very similar to 30 grams per mole. So that variable has now been equalized, and now let's take a look at its boiling point. In this case, about 65 degrees Celsius. That is about 85 degrees above that of our representative molecule bearing dipole-dipole forces, a huge number. Again, this is a stunning testament to the much greater strength of hydrogen bonding than in a molecule compared with a representative molecule which only bears dispersion forces. Again, if we would find that, if we looked at this molecule, it doesn't just bear hydrogen bonding, it also bears dispersion forces, and we would also find, if we were careful, that it would also bear dipole-dipole forces. But when we look at it, by far the greatest contribution to its strength of intermolecular forces is from hydrogen bonding, to the point where it's no comparison. The other two within this molecule, dispersion forces and dipole-dipole forces, while present, are insignificant. Hydrogen bonding, as shown by that boiling point difference, blows them both out of the water so that we don't even consider their contribution. We essentially say this molecule on the bottom's primary intermolecular force is that of hydrogen bonding, and that is enough. So let's take a comparison here. I have a picturesque graph over here on the left-hand side where I have compounds of very similar mass made up of carbon, nitrogen, and oxygen, all with their attendant hydrogen atoms attached to them. So what we're going to be doing here is looking at this comparison of molecules containing hydrogen or exhibiting hydrogen bonding with those that do not. So we have, if you look at the periodic table over on the right, I have representative compounds of carbon, nitrogen, and oxygen. Nitrogen and oxygen, we know, have hydrogen bonding associated with them. Carbon does not. Any CH bonds, for instance, do not hydrogen bond. NH bonds do, and OH bonds do. So let's look at that. So if we look at the graph again over on the left-hand side, on the y-axis we have temperature. We're basically talking about boiling point, increasing boiling points. So we follow, in this case, the boiling points of our representative molecule with oxygen versus nitrogen versus carbon. So our representative molecule versus made of carbon, in this case this is a hydrocarbon, has a boiling point of about minus 160. Fair enough. The representative nitrogen compound has a boiling point of about minus 15 degrees Celsius. A heck of a lot higher than minus 160, which is a testament to the strength of its hydrogen bonding. Water, on the other hand, as I said before, water was just one large walking hydrogen bond. It has a boiling point of 100 degrees Celsius, very far above that of nitrogen, which is curious. In any event, we'll explore that later. Let's look at our representative molecule, water, right here, with 100 degrees Celsius boiling point. Now we'll look over on the periodic table on the right. What's right under oxygen in the periodic table? That is sulfur. Sulfur is much heavier than oxygen, but it can't hydrogen bond. Here we have H2O up on the left-hand side. What if we replace that with sulfur to get H2S? That's a heavier molecule, greater molar mass, but we have an attendant very strong decrease in our boiling point, meaning that the particles of H2S, even though they're much heavier, have less strength to their intermolecular forces. A testament to the strength of hydrogen bonding. Water, being much lighter than H2S, has a much higher boiling point. Why? All to do with the fact that water, H2O, can hydrogen bond and H2S cannot. We see the same thing with our representative nitrogen-containing compound. It has NH bonds. That means it can hydrogen bond. If we look over on the periodic table on the right, look right under nitrogen. What's under nitrogen? Phosphorus. Well, let's make the corresponding phosphorus compound from nitrogen, NH3. Let's make PH3, a much heavier molecule. Phosphorus is much heavier than nitrogen, but again, we have an attendant decrease when we compare their boiling points. Why is that? Again, it's because NH containing molecules can hydrogen bond. pH containing molecules cannot. So, when we started out with a particle, a molecule that can't hydrogen bond in the first place, carbon, look over now at the periodic table on the right. What's right under carbon? Silicon, a much heavier element. Going from CH4 to SiH4, now we get that attendant increase in boiling point solely due to the increase in molar mass that we saw before in particles which only bear dispersion forces. And in both the cases, hydrocarbons and silicon compounds only bear dispersion forces. But let's get back to that unusual sort of anomaly we saw before. If particles containing NH bonds or OH covalent bonds can hydrogen bond, And these particles over here on the left, H2O and NH3, are about the same molar mass. Why is there such a difference? Such a difference in their boiling points if they can both hydrogen bond. There's about 115-degree difference between them, and they weigh about the same. What's going on? Well, we can only arrive at one conclusion, and that is the correct conclusion, and that is that NH hydrogen bonding is generally weaker than OH hydrogen bonding. That's just a truism. And we can, again, compare two different molecules, one containing NH bonds and one containing OH bonds. And let's look at the molar mass of each of these. They're about exactly equal. However, looking at the boiling points of them, the NH containing representative molecules about -7 degrees Celsius boiling point, whereas the representative oxygen or OH containing one, both can hydrogen bond, remember, about +65 degrees, a huge difference in boiling points. And this again is a testament to the fact that OH hydrogen bonding is stronger than NH hydrogen bonding, or if you like, you can turn it around and say NH hydrogen bonding is generally weaker than OH hydrogen bonding.